Hello. Hello.
Yes, ma'am.
Yeah. Am I audible? Yeah.
Yes, ma'am.
Okay. Okay. Fine. So let's start our discussion today. Before that, there are two questions actually you asked last day that we couldn't answer. First one is someone asked about the grading policy, right? So for thing is that we are planning to take two exams before midsem and two before nsem. One is will be like online viva sort of thing. We will take some online viva, and another we are planning for written exam that your video will be on, and we will be monitoring remotely, and you have to give the exam. So these are the two ways, and of course there will be some continuous assignments. So this is the plan for grading this time. This is one thing. Another thing is that another question was there, some technical question. Wait. Last day someone asked why ARM is preferred in case of mobile like advanced like platform. Right? Some maybe who has asked, I don't remember. But to answer this question, I just want to ask you, you know about the difference between CISC and WISC, right? CISC processor and WISC processor? Yes or no? Just reply in the chat if anybody
Yes, ma'am.
knows, right? So if we consider CISC type of instruction, or rather RISC type of instruction, the main advantage is it is, as the name suggests, of course, it is reduced instruction set completely over CISC. And when it was first proposed, I mean, when WISC came into picture in the initial days, that time WISC promised some power efficiency. I mean, in terms of power, there are different optimizations WISC processors included that promise to be power efficient in smaller platforms. Specifically, that is the reason why ARM, these type of, RISC processors dominated this mobile or Android technology. Where in case of x86 or these type of, in these scenarios, they generally use 6 type of architecture. This means it's complex instruction set architecture. So in that case, these power efficiency actually when we cannot say now x86 is not power efficient or something like that, because now there are different power efficient version of x86 is also coming. But when it was first proposed, initial it was proposed for desktop computer, and people know that we have some wall mounting power, and from there is no thought about how to efficiently use the power, or it was not a major thought that power can be a concern. So when these processors we were using in embedded platforms, then power efficiency took a major role, and that time this type of or RISC-based this type of processors came into the leading part. So this is the major reason why these x86 was not preferred when we consider this mobile computing scenario. Okay. So these are the two questions. Do you have any questions regarding?
Regarding the exams, you said that they'll be near the midsem and nsem, but we don't have a midsem and nsem this time.
No. Exactly. We do not have exactly midsem and nsem, but what we are doing, we have actually divided the course in two parts, as I have explained yesterday. In the last class, where we have explained that some part I will be taking, and some part Professor Sharkar will be taking.
Okay.
Okay. So in that part, there will be two exams, and in Professor Sharkar, he will be also conducting in his part two exams. One probably one will be written exam, and probably one will be online exam. Okay.
Could you also give the breakup of the exams and stuff like that, the intricacies?
Exam intricacies. Okay, first you start with the course content. First, let's discuss, and then we will start discussing what will be possibly covered.
Okay, yeah. Sure.
Okay,
Thank
so
you.
just start with this. So with that, let's start with today's discussion. I'm sharing my screen. Just let me know where you see the slides. Is the slides visible? Hello?
Yes, ma'am.
Okay, fine. So today we are going to discuss about computational models. If you remember our previous discussion, there we already talked about what are the challenges in present embedded system design. We talked about that we have some particular specification, and from there we want to come to the actual implementation part. But since today's ICs are getting cheaper, we can actually incorporate huge number of processes in one IC. So all these things making this embedded system design more complicated. So sorry, just a second. So this is the main reason why we have actually introduced one extra step in our discussion, that is the computation models, and what computation models will be suitable for different types of embedded system design or cyber physical system design. So this is what we have already discussed, that embedded system processing behavior is becoming complex, and you can see this part is basically important. Whether you can see it, that embedded system now and then. When initially embedded systems were proposed, we use small embedded parts in our maybe washing machine or in our household application. The number of codes what we were dealing with was very small. Then we have moved to digital cameras or more complex embedded applications where the number of lines of code it was more, and it was around maybe 100,000 lines of code. But nowadays, what is the complexity? Nowadays, we do not think about simple one or two modules, one or two embedded systems. We think in terms of overall embedded network. Like you can think about this example. Just take 1 minute and read this example. Here we are thinking about a city where we are basically trying to develop V2I architecture. Now, probably you have heard about V2V communication. V2V means vehicle to vehicle communication, where we expect smart cars, they are communicating with each other. Now, this is also, this is an ongoing technology that we are trying to implement. Along with that, we are not only satisfied with V2V, only vehicle to vehicle communication. We also want vehicle to infrastructure communication. What does it mean? When there is a street traffic light with in the communication path, that will sense the presence of some pedestrian or some presence of some vehicle, and according to that, it will change its signaling technique. Also, the cars will cooperate in this case. They will detect infrastructure situations. Hello. Yes. Okay. They will detect the infrastructure situation. They will detect directly if there is any pedestrian on the path. They will directly detect what is the signaling situation coming from the traffic signal, and based on that, they will also adjust their states. So this is basically not only vehicle to vehicle communication. This is, we can consider as vehicle to infrastructure communication. So now we can consider so many modules, so many controlling interfaces, so many control-based communication we have to take care when we are actually designing, we are actually taking up one embedded system-based project. Next, another example.
Can you put the slides in full screen? Like, can you start the slideshow?
Yeah.
So it'll be a little bigger.
Yeah. Oh. Fine. Okay. So in the next example, we can give in the medical domain. How we are changing the face of the medical domain with the help of embedded systems. This is an example of heart surgery. Where in case of different heart surgery, it is required to stop the heart and then to perform the surgery and the restarting of the heart. Now, this is very critical process, and there must be some significant, time. You have to perform and complete the process with the significant amount of time, and something more and less can be detrimental. Now, of course, we are trying to make it more sophisticated, where we are trying to introduce robot intervention in case of handling these surgical tools. Or the way of surgical pattern is also changing when we are planning to do some video systems simulation of video system simulation, where the doctor will actually think that the heart is actually at rest. Without actually stopping the heart, they will plan to perform the surgery. So all this surgical tool invention and this controlling of the surgical tools through robotics, you can understand these are also required huge number of embedded system based, actually embedded system network development, not a single embedded system development. So for this reason, we have to take the help of computational model. Now you can see that when we define this computational model, or when we consider this embedded computational model, what we actually consider? We consider some set of objects and what are the rules we are defining to control or communicate to defining the communication between those objects. So based on that, there are different types of models in literature, and we have to choose the perfect one that suits for our embedded system need. Now, what are the different typical models? First one, and the most simplest one that we mostly use, is the sequential program model. Now, I hope you all know about C programming and how to write sequential codes, sequential instructions in C code. So what do? We first decide what algorithm. First, that algorithm comes from certain specifications, and based on that, we define some instructions, and those instructions we write step by step, and those instructions get executed sequentially. So basically, it is handling with some set of statements. Now, next you understand now when you are going by the sequential program model based technique, it is not only one sequential program model you can define or design. Because see, if I again go back to that V2I networking example, there you have to design some sequential model for the car, smart car. You have to define some sensors related to the pedestrian. Maybe you have to define some sequential model for that traffic light control. And of course, all these sequential models must be communicating with each other. So there must be some support, to describe how this communication will take place. So for this reason, we need to have another communicating process model. We need to have another model that is called communicating process model, where these sequential programs or sequential processes can communicate with each other. Next, we will see that another approach that is called state machine model. This is mostly useful for control dominant systems, and there are few advantages of this state machine model over sequential model. I'm not going here in the deeper because today we will mostly discuss in detail about this state machine model. So let's see what are the other models. Another model is data flow model that is mostly used in data dominated systems. What does it mean by data dominated system? Let's say when you are considering some in-stream flow of data, you have to do some processing on that that data, and you will get the output. For example, when you are performing some filtering functionality, noise filtering, so that in the filtering cases, you just focus on the input stream and perform some filtering on that input stream, and you can get your output data. So this is the example of data flow model. Next, what is the type of model? Object-oriented model. So these are few different models possible in literature, and we will take one by one with some examples, and we will see how it is useful in our embedded system. Today, we will mostly focus on state machine model. Before that, one important thing. Why we are designing a model? A model basically giving some abstract idea about a system. Now, this model, you can tell if it's how high fidelity, if it accurately describes all properties of your system. But in actual case, this is not possible, because there must be some abstraction in the system, and then leads the requirement from your system modeling to your system modeling for system design. Because you understand, right? Every technical implementation nitty-gritties that you cannot actually implement in your model, but still we want to have a deeper look compared to specification. We want to have a deeper look in modeling, but that is before implementation. The second thing is that when you actually want to realize the model, evaluate the model, you need some language. That means when you have done a modeling, of your system, of your problem, and that modeling should be mapped to some language to be evaluated by some tool. All the existing modeling tools are based on some languages. Now, when we are talking about sequential program model, of course, we can mention about C, C++, and also these are mostly software-based approaches, and VHDL and Verilog, they are mostly important for hardware-based design. When we go for feature-based design or something like that, we mostly prefer this VHDL or Verilog because of their constructs. Okay, whatever construct supported by these VHDL or Verilog, you will see actually those who will be doing that ESDV lab, there we will be basically starting with the C, C++, these examples of modeling, and then we will gradually move to this VHDL and Verilog. There we will see what are the different constructs. Those are supporting some advantages in terms of hardware design that is not present in C, C++. That's why these VHDL or Verilog, those are mostly preferred in case of hardware design, or when we go for hardware software coprocessor design. Maybe you remember in our introductory lecture we have just introduced what does it mean, this hardware software coprocessor design. So anyway, the important part is that you have to map a model to a language to be evaluated by a tool, because the tool will give you the evaluation support, debugging support, and simulation support of your model. Now let's start with the sequential program model. Now, one thing I want to do is so in the sequential program model, we will start with one example. we will take the example of simple elevator control system, where we will first try to get the specification. Then we will see how we can realize them in sequential model, and we will see what can be the disadvantages or advantages maybe in the sequential program model, so that we will be moving again to the next level of modeling technique, that is FSM or state model. Okay. So just if you think about a simple elevator system, what are the control inputs you can think? Of course, the control inputs may be the floor buttons inside the elevator when someone is inside the elevator, or someone is waiting outside to, to get the elevator. He or she may press some up or down button based on his or her preference. So this up and down button from outside and the number of floors that can define my destination inside the elevator, those are my control inputs. What is the data input? Data input will say that representing the current floor of the elevator. And then what will be the control output? Control outputs will be based on my choice. Like if I am in third floor and I am pressed to go to maybe floor number 5, so the elevator will move up, or if I want to go down, it will go to I want to go to ground floor, it will go to down. And also based on my selection or based on my preferences, whenever my chosen floor will come, the door of the elevator will be open, otherwise it will remain closed. So all this will be mapped to my control outputs. Now let's see what can be my English language specification. You can see in the left, this English language specification shows that move the elevator either up or down. I'm just reading whatever given in the specification, nothing else. Move the elevator either up or down to reach the target floor. Once at the target floor, open the door for at least 10 seconds. So these are the typical specification details, that is how much delay that will actually control your modeling or implementation. So you have to at least open the door for 10 seconds and keep it open until the target floor changes. Ensure the door is never open while moving. Don't change direction unless there are no higher requests when moving up or no lower requests when moving down. Now you observe the specification. This specification gives you mostly two things. One is that what are the control inputs or outputs you can choose. You can see in the right hand side, we have actually considered two modules or units, unit control and request resolver. I will come to that those modules afterwards, but first focus on the control inputs and control outputs. So as we have already discussed, this up, down, open, those are the control inputs or outputs. And floor is a data input, where we want to actually go, or where we are currently in, that is the floor. Next, here the buttons B1, B2, Bn, those are the inside buttons, and this is the and this up one, up to up. So up, down, those are the buttons that specify where, in which direction we want to go. Now, when you are modeling this technique, you have to first understand what are the modules will be required to handle this specification. Now, if you want to model exactly this specification, we are splitting this model into two parts. You can see these lines. move the elevator either up or down to reach the target floor. Once at the target floor, open the door for at least 10 seconds and keep it open like that. So this is something related to your unit control. These is a part of specification we are handling in our unit control. That is, when I have got one exact request, I know to which floor I will go. I know whether I am going to up or down. Based on that, what I will do. Okay, I know what is my perfect destination floor. So based on that, then after that, what are the steps I have to take based on the specification that I will handle in this unit control. Okay. Now request resolver is something different. See, don't change directions unless there are no higher requests when moving up or no lower requests when moving down. This is something when you have not actually fixed the destination, or you have actually fixed the destination after maybe some requests are coming. Maybe there are 5 people in the elevator and they already pressed different destinations. Some already pressed 2, then some already pressed 3, and some already pressed 5. After that, some person pressed 4. So now there are multiple requests to this elevator system, and based on this multiple requests, how we will consider the final next request. So that will be handled by this request resolver. Basically, request resolver will be the first module to get executed. That will take multiple requests, and from that will actually finally decide the final request. Final which floor I will consider as a target floor. And that input will be given, you can see, will be given to this unit control. And after that, we will see what will be the instruction steps we should mention in this unit control. Okay. So here in this model, you can see that we have already mentioned our inputs will be that up, down, B1 to Bn, and bit up, down, or open to check whether it is going up, down, and the door is open or not. So let's take the steps of the unit control. Where you can see that we have in this up is equal to down is equal to 0, and these steps, this is nothing but the initialization step of our control inputs. After that, based on the change of the values, we will actually change the value of other variables. So here, while actually there is a mistake here, while request not equal to floor, open is equal to 0. That means when that requested floor is not equal to your current floor, that is whatever is requested, if you have not reached to that floor, then open, the door will not be open. So that open will be 0. Otherwise, next if it's telling you if request greater than floor, then up is equal to 1. That means if your requested floor, maybe you are in floor number, current floor is second, floor number 2, and your requested floor is 5. So 5 greater than 1, 5 greater than 2. So up is 1. That means your elevator will move to upward direction. Else it will move to downward direction. Then while request is equal to, here is another mistake. Basically, it hasn't swapped between these two whiles. Here this while request is equal to floor. That means whatever requested floor you have mentioned in your request variable, REQ variable, and your current floor number both are same, then open is equal to 1. That means now your door will open. Then you are assuming that there is a support of one delay function. Then delay 10 means, remember your specification in the previous slide, that open the door for at least 10 seconds. So here with this delay 10, We are basically satisfied with that specification. And your door will remain open for the 10 seconds or whatever the specification may be. Then again this while loop will continue because you have written everything inside a while one. You can see after initialization stage we have actually written one while one. So every these states, every these instructions will get executed continuously, and to incorporate that in your model, we have introduced, we have written this while one step. Okay. So this is the basic step what you are going to write when we are actually mapping your specification to your sequential program model. Similarly, you can write this resolver. And the important part is that in void main, you can see these two, this unit control and this request resolver will get a concurrent call. That means they will get executed concurrently and should communicate time to time. So this is the basic idea how you are actually translating your specification to a sequential program model. Now, what is the limitation of this model? It may happen when you have actually written these if and states, if request better than floor, else, etc. Maybe this is a very simple design we have considered. But when we are gradually moving to complex designs, complex modules, and those modules are communicating, maybe some set of instructions in this process, there is a tendency the sequential program model is designed in such a way that it may happen we miss some communication or some instructions in this sequential flow of describing your specification. Compared to that, state machine model is considered a more defined approach. You can see the state machine model means we are defining some states. State means some possible system occurrences. We will define state machine or final state machine later on in a more formal way. But now just understand the concept. State means system occurrences. And every possible state, when you are considering every possible state, we must consider what are the objects associated with it and what are the interactions going on between them. And they will actually affect to define our input control and finally our outputs. Now this is very straightforward idea. Since you're defining your system through these states, so if part of your system is not secure, your whole system cannot be secure. But I'm not going to this line actually because there is different meaning of security. So there is altogether a different discussion. But of course, to design a secure system, what you have to consider, we have to consider all the associated states of that system to be secure. So in that way, if we again think about our previous example, that is the same elevator example. Now we are understanding, we are modeling that same problem with a different approach, that is a state machine model approach. Here what we have identified, you can see here we have first identified these states. This is the going up, idle, going down, door open. These are different states. And here you can see before going up, we have some request greater than floor or request less than floor, equal, not equal, is the timer less than 10. All these are some transition conditions. Based on that condition, we are basically making a transition from one state to the other. In the left, you can see UDOT. So these are some Boolean values given 1, 0, 0, 0, and so these are basically your up, down, open. Those are control inputs. And these control inputs is defined by 1 or 0. You are actually checking whether your elevator is going up, trying to go up, trying to go down, etc. So that way, if your elevator is in the going up state and your requested floor is greater than the your current floor, present current floor, then what we will do, you will continue to go up. That means your state machine will remain in that same going up state. So see, there is one self arrow, that is a indication of self transition. That means whenever you are in the going up state and the condition request greater than floor, that condition is getting satisfied, you are in the same state. Similarly, if you assume that your elevator is initially in the idle state and then you are basically getting a request to go up and down, then only that idle state, based on their given input, given request input, it will you check the condition request greater than floor and it will be going up, otherwise it will be going down. Similar self loop will be there. Self transition is possible when you are in the going down state and your request less than floor condition is getting satisfied. Similarly, there are some conditions should be satisfied when you have to go from going up to door open state. Okay. So this way we can see when we are actually defining this state transition model, what you have considered, we have considered the possible system occurrences and we have defined those states. Then we have considered what are the transitions required to go from one state to the other state. And for that, we have to define the transition conditions and also the control inputs. So this is one typical informal idea of how from one specification we can move to a sequential model, and then from sequential model we can move to our this state machine model. Now this is the formal definition of what we mean by state machine or finite state machine. Do you have any questions so far? Because
Pardon? Excuse me, ma'am.
Is there any question?
Am I audible, ma'am?
Yes, yes. Yeah, tell me.
Yes, ma'am. In the state machine model, if simultaneously two people will enter, someone will enter up and someone will enter down, what will be the flow of that algorithm?
Yes, that part here based on the time lapse, see, we have already discussed in the request resolver. Okay, this request resolver will take those two inputs. Okay, and that they will actually, whatever algorithm we have defined or you have preferred, maybe there are some some previously set notion that maybe if up is pressed and down is pressed, up will be given a preference or down will be given a preference. These type of predefined notion should be incorporated in this request resolver, and that is the functionality of this request resolver based on those that notion, because first it will check which button was pressed first. If up is pressed first and then the down, and there is a time lapse, then the decision is very easy, right? The first come first serve basis, maybe we can prefer the first. But if that is not there, in complex scenario, we prefer some set notions. We input some set notions into our algorithms, and based on that, we set some priority in those buttons. So if the priority thing is my set notion and set priority says, okay, you give preference to the up or you give preference to the down. So based on that, the next converse ifs will take place, will be considered actually. Okay, is it clear?
Yes, ma'am. Yes, ma'am.
Okay. Any more questions? Okay. No, right? There's nothing I can see in the chat. So now this is the, now we will formally define what we mean by finite state machine. Now in finite state machine, you can see here, oh sorry, so in this finite state machine, you can see FSM is defined as a fixed tuple. What are the members of that tuple? The first one is S is a set of states, A0 to Sn. Maybe we are considering there are maximum L number of states. So S is a set of states with starting from S0 to S0. I is a set of inputs. Those are maybe my control inputs that we have already discussed in our example. O is a set of outputs. So in some cases, these set of outputs may be a state. In some cases, these set of output or set of outputs may be a transition, maybe some transition. Some cases, we have to define value of some variables as the output. So based on that, there are different classifications of this FSM. We will come into that. But this O can be anything. Your state can be mapped to some output. Some transitions can be mapped to some output, or setting of some variable values can be mapped to some outputs. Next, F is a next step function. Basically, this you can think about the transition condition, based on which actually your one set, maybe from this A0 to SL, will be moved to next set. So you are taking input from a set, that is your current set. You are taking input from your inputs, and then based on these two, you are making the decision what will be your next set. Of course, that next set S is also, the next set, it is also same as your state of states. Your next state is also coming from the whole set of states. And H is an output function. That is, what is the output of your FSM? Here we have just, according to these definitions, you can see that your current state you are mapping to your outputs. That means S is mapped to O. But this is not always the case. This is basically the example of more type of FSM. We will come into that later on. There are the other many type of FSM where we will be mapping some transitions to outputs. But for the time being, let's consider these definitions of FSM. Oh, S0 is the initial state with which you are starting to evaluate your state machines. So this is basically these six. This is the definition basically of FSM with the six tuples, where you are considering set of steps, set of inputs, set of outputs, transitions, set of outputs. Output function, and your initial state. We will take separate examples for this more and we will explain that later. Now, this is when I define that you are basically mapping these sets, some current sets, to your outputs, or you may define some variables as your output. But if you can see again, go back again to this definition, you can see that we have not defined or augmented any variables in the basic definition or standard definition of FSM. But So remember the example we have discussed in the previous class. You remember the GCD example? There what we have done, we have written the source code, instructions to execute that GCD, and then we have divided that to different states. We have considered few control inputs, and we have also considered another additional part, that is the data part. But in traditional FSM design is basically to define any general control input based system. It has not considered the data path itself. So this FSMD, or when we will be considering the inputs from data path to my FSM, that is basically one extension of FSM to support this complex scenario of embedded system. So basically we will take this another example also, and we will see how FSMD or this extended FSM will be meaningful to actually design the our state machine in case of embedded system design. So in this FSMD model definition, we can see how we are defining. Basically, the definition is exactly the same. We have that same set of input states. We have that set of inputs. We have that O is a set of outputs. We have this is the extra thing we are considering here. We are considering a set B, that is set of variables. Now these variables we will be considering in our state transition conditions, and these variables we will be considering in our output decision making. That means here again this next state function, or we can say the transition condition, is also changing. If you remember in our traditional definition of FSM, we have only considered that my transition condition will be based on my input set, my inputs, and here we can consider some other variable values, maybe that is coming from my data path, and that will, these three inputs together will define what will be my transition from my current state, maybe Si, to my next state, Sn. Okay. Then this one also getting modified, that is the H is an action function or the output function that is defining by my output. And when we are defining this output function from my from a particular state, again here we have considered that we are mapping some state to some output. That is a very typical type of Moore FSM. We will take another type of MLE FSM. But here we have considered one particular state. You can see that is getting mapped to one output, that is defining one output, and along with that, that is also defining some variables from the set of variables that is defined by V. So basically, when we are considering this FSMD model definition, we are not only considering in the output part only the output state or some state value, we are also considering some particular value that is getting set by this transition. And S0 is the same, whatever we have already considered previously, that is the initial state. So this way, with the introduction in data path in my design, we are also incorporating the effect of data path in my FSM modeling technique. Now we will maybe just now take this definition step by step. At this point, we will take one example and we will explain how this introduction of variable in FSM is actually meaningful, actually very advantageous. We will take one example, and I think that time it will be more clear. So now I hope you have got some basic idea about what do we mean by state machine model and what do we mean by sequential program model. Sorry. Now, is it? Now the question is, yes, when we are considering state machine model, we are thinking that we have defined all those states, and now since we have those states, if we properly define all the state transition conditions, it is more well designed or more well structured in comparison to sequential program model. But if we actually consider all the instructions properly in sequential program model, then typically there should not be any difference between the state machine model and sequential program model. Basically, this is two different ways of thinking the same system behavior. But what is the limitation if we directly prefer this state-based model? I mean, not state-based model, this FSM-based model. Whatever tools we have, the existing tools when it was first proposed or nowadays also, if you consider those tools, they are basically based on some programming languages. Now, these programming languages, maybe it may be C, C++, Java, whatever it may be, but those also directly support these sequential programming techniques. An interesting part is that there is not much tools developed so far that directly support these states as a construct. Like you can consider these states as a construct. Like your construct means I hope you understand, right? In language, like you can use the state as a construct and some transition as another construct, and then you can actually realize your state-based model in your tool directly. So that's why it is important that initially it was an important question. Now it's fine that you think the state machine model is more defined, more structured. You have defined your system with the state machine model. But how can you map them to the tools? For that, you have to take, you have to take the help of these sequential program languages. So this is the another example. In this example, we will see this. We will come back to this our same state model, and here we see how these state model we can realize with our sequential programming technique. Because we can see there are some advantages in both the cases. In state machine model, we are getting more defined model, more distinct model. And in sequential programming language, what we are getting a direct mapping to our existing tools. We can get an easy way to evaluate whether my model is working fine or not. So for this reason, here our next step is, when we have already designed this state machine model, we are going to other way around. We are trying to realize these state machine models in terms of sequential programming language. Now you can see here, you can observe this unit control function again, but it is written in a different way, where we are using this construct switch, and this switch is basically taking the input states. So whatever states we have defined in our state machine model, like going up, idle, going down, door open, etc., these are the states. We are considering these states as a switch, and with this, in every state, we are defined what value we will take as control inputs, and in this if construct, we are checking basically the transition conditions. So if request is equal to floor, what I will do? I will be in the state idle. If it is greater than floor, my state will change from idle and the next state will be going up. So within this if construct, we are considering this transition conditions, and based on that, we are defining what will be my next state and how the state transition will take place. Similarly, in case of if the state value is going up, based on that, I'm taking up is equal to 1, down is equal to 0, open is equal to 0. These are the all control inputs. And again, within this if, we are considering this transition conditions, and we are moving to next state like going up or door open, and so on. You can see the same thing for going down or door open, same notion has been applied. So this is the typical example how we have already from the specification, we have identified the states, we have defined the state transition conditions. Now we are evaluating that, maybe we are first writing them, those state or state transitions in terms of our sequential programming language so that we can evaluate them with our existing tools. Okay. So this is a general template that we have already discussed. Now I think it is will be just a repetition where my switch will take the value of different states, maybe S0 to Sn, whatever number of states you have defined in your state model. Within this if construct, we are considering, we are actually checking our transition conditions, and after that, inside every switch case, we are defining what will be my next step based on the conditions, so satisfied or not satisfied, whatever it is. So this is the general template how we are actually taking a practical model, practical system specification. We are translating them to some state model, and then from some state model, we are actually moving to some sequential programming. And with that sequential programming, we are trying to evaluate that model. This approach is basically called a language subset approach, where language subset approach. So where we actually consider this, we are actually setting some strict rules to capturing the states, and then based on those defined states and state transitions, we are moving to our sequential programming model. Now, this is one basic example we have considered where we have actually introduced two types of models. One is sequential, one is state machine model. And we have seen a flow how we can, from a practical example specification, we can go up to the two-level simulation. Now the question is, when we are considering any embedded system, we have to deal with different dynamic behaviors. And also, in embedded system, it is not that we are just considering some continuous dynamics, or we are just considering some discrete dynamics. So embedded system means it will be amalgamation of both. So what will be the possible modeling techniques or suitable modeling techniques or approach we should take in this embedded system design scenario? Now let's start with the simplest one, that is if you consider something with continuous dynamics. I'm not going into the deeper of this because it's known to you, I think. Whenever you are going to model some mechanical parts or some mechanical dynamics, general physical dynamics, what we do, especially in continuous time system, what is the general approach? You just take ODEs, right? Ordinary differential equations. So that is very basic. I think whatever you have already learned. So from this ODEs, we can directly jump into a modeling technique that is called actor models. Now, what does it mean by this actor model? This actor model or actor models are nothing but the mirror of this ODE. Let's take an example that will share your idea. So in this modeling technique, this is one helicopter example, but nothing to do with that. Just focus on this general equation. I think these type of general equations you use in different scenarios when you are actually defining one physical system with continuous dynamics. So here, whenever we have such type of equations, we just identify the actors. What does we mean by actors? The main computing portions. So here, this is the integrator part. So from this, we are basically designing this integrator actor where my input is, you can see this is the input part and this is the output part. That is quite straightforward. And in this integrator, we are just putting this initial parameters and maybe this is initial related other parameter as integrating parameters. So this way, this is the actor model that just can directly replace or directly model this ODE. And these type of actor models, this is an integrator actor. It's readily available in your different embedded software design tools. And also you can use them as a cascaded composition where you have this one composition and these two actor models, they are readily cascaded together. Now we can take another example of this cascade composition where we can see this is a gain or scaling actor and this is one integrator. So this is the left actor represents the scale actor where if this is y1t is equal to ax1, you are incorporating the scaling factor here and based on that your scaling factor, your actor model is basically computing this part. Similarly, the right actor is an integrator where this integrator is taking input as this x2 and this is your output and it is basically taking this I as your initial sum parameter. So this way you have some ODE, you have some mirror like actors that can directly represent these ODEs. So this is one simplest modeling technique that is still now supported in different LabVIEW, Simulink, those tools. But we will see that is the most interesting part. So is this actor model based technique or modeling technique suitable when we are actually talking about some complex embedded system? Or why, maybe the question will be like that, why FSM, we will discuss again, is still suited and still well accepted technique in embedded system modeling compared to these existing models, maybe sequential model, maybe actor model, still those were there, still FSM is mostly accepted technique when we are considering this embedded system scenario. So this is another example. With this example, actually, we will again explain our view. So this is the example of one car garage, smart car garage we can think, or smart car parking scenario where whenever you are entering inside the car parking, you have one arrival detector that is counting how many cars are there. I mean, how many cars entered inside the parking lot or the garage, and it is increasing the count. It is maintaining one counter, and it is increasing the count to count plus 1. And whenever any car is leaving that parking lot or the garage, there is a departure detector. This is the departure detector that is basically down counting the counter, so that the total number of vacant places, car parking places, can be displayed in a outside display. So I think this is very common, and you have seen in different car parking lots and scenarios nowadays. So to model this, if we think with our existing schemes, like if we start thinking of modeling this scenario with our existing active models, is this, what we will do? First, we will take our discuss our approach, and then we will check whether that is sufficient or not. So, okay. So what we have this. We have this counter. Okay. Now, what this counter is taking? It is taking constant input from your arrival detector or your departure detector. So this counter is basically adding whatever input is coming from the arrival. Now this adder can be replaced with some integrator. So what we can think? We can actually replace this counter with some integrator, and we can check whether it is correct way of modeling or not. So what is the problem here? So can you identify the problem? Someone? Hello? Hello?
Yes, ma'am.
Yeah. Can you identify the problem? Are you there with me? Are you listening?
Yes, ma'am. Can you open the slide page?
Yes. So I'm suggesting that this counter, can I replace with the integrator? If yes, is there any problem? Do you think there will be some problem?
Yes, ma'am. The counter is simply counting. When there's something in the arrival detector, then it is adding up, and when there is something in the departure detector, then it is subtracting that. But integrator won't do the subtraction part.
Okay, and if we give some negative, okay, let's forget about it. Let's forget the departure part. If I give the only arrival detector, and at that time, if I replace that counter with this integrator, is it fine?
Ma'am, we consider practical aspects, because if we are using an integrator, there is a possible of integer overflow of something of sorts.
Okay, so that is another thing, another direction. But let me tell you, if we don't consider, maybe there is no integer overflow or those sort of things.
And ma'am, for integrator, you need a continuous time signal. Discrete signal won't work.
Exactly. For that is the problem. So when you are planning to, because whenever you have to model, you have to think about whatever I have in my hand, right? Whatever I have in hand, that I have to use it. So this counter, if I replace with this integrator, what I have to do? I have to think about some continuous time sequence. But this counter in practical scenario, that is basically event driven, right? Event driven. That means whenever any event is occurring, whenever any car is entering inside the parking lot, one event is occurring, one event is taking place, and that event is sending some signal to your arrival detector sensor. That sensor at that time is sending these input up. Or similar thing happens when there is a detection in the departure detector part. So basically, this counter is event driven. So whenever there is any event, at that time only, this counter is working, or this counter is, I should say, functioning. But if you are actually using some integrator, what is the cost? When there is no input. So maybe there is no up counter update or down counter update. At that time, there is no proper input. So you have to define some input as absent or something like that. And then you have to some value of that absent part you have to send to the integrator because that is continuous time driven. So that means for a discrete signal, if you are choosing these type of active models, that is wastage of your resources. That's why whenever we are considering this discrete system, at that time, it is these active models are not suitable. And at that point, we are moving to this notion of state where we are considering some state and some state transition conditions. Most importantly, we are considering that whenever these state transition conditions are not present, are not satisfied, then my system, finite state machine, can return in that exactly same state. So these discrete dynamics can be better implemented, better realized when we move to this state machine based model or finite state machine model. So here we are basically mapping each reaction to my input guards, and then we are deciding my actions. Now, what we mean by this guard and action, you can see in the diagram that so far we were talking about these transitions. And in state 1, we have already mentioned this initial state indicator. And now we are talking about these two new terms, that is guard and action. This guard is nothing different. This is same as your transition condition. Remember, we have defined that if function, that is my transition condition, and that is, you can call it guard. And what is the action? This action is defining what is the, when we are satisfying this guard or satisfying these conditions, what next step we can take, or what is the action if guard is satisfied or not satisfied. Now you can say, ma'am, obviously, whenever I am in state 1 and this guard is satisfied, I will go to state 2. So why we should keep this extra action part here? What is the importance of it? Now, when we are actually considering a straightforward FSM, I mean, classic model of FSM, of course, mentioning this action separately or not, actually, there is no added value of it. But we will soon explain some example of FSMD or extended state machine. there you will see that if some condition or guard we are deciding in such a way that when there is a state transition from state 1 to state 2, maybe guard 1 will get satisfied, and along with that some variable v1 will be set. In that case, maybe that variable v1, v2, whatever vi is not the part of state 2, that is some other variable. That time that variable or the setting spatial value to that variable we can mention in that state, in that action part. So along with this transition, these variable setting or variable handling, or rather we can say variable augmentation, is better handled in this guard action representation. Okay. Now take the example again. We are back again with our example. So in this example, you can see we are redefining our FSM model. We are defining this garage counter or parking lot example in this FSM way. So you can see we have defined these states 0, 1, 2, 0, 1, 2 up to this M. These are my states. So M will be maximum number of parking lots or vacant, total number of vacant places present in my parking lot. So initially, if the total number, there is no car in that parking lot, I will be starting my transition from 0. Next, a transition is taking place where I'm checking which condition is getting satisfied. If my control input up is 1 or it is not down, then we are actually going to my count 1. That means state 1. Similarly, when my up is 1 and not down, then I'm going to 2, 3 and so on. Similarly, the reverse part, maybe when the count, that means existing cars, the present car, the count of cars in the parking lot is 2. At that time, if some maybe arrival or departure detector is detecting some event, at that time this control input is coming to my model, and that time I'm checking is that these condition getting satisfied. Is it that down is set or it is not up, then I can move to next step 1. Right? So this way I am taking the transition from one step to another. But remember, there is a challenge in this case. In this case, whenever we have considered this example initially, we have considered this number of counts possible inside the parking lot as my number of steps. And based on that, we have decided my transition conditions. And based on that, we have considered these guards and we have considered this action. Action means, in this case, we are moving to state 1. Next step as count 1. So that means the count, the value count we have considered as state, and we have designed our transition conditions. Right? But can you identify any problem in this? In this design model or in identifying the state in this way? Do you think there will be some problem? Shall be one unique peak. It shall not be. Okay. So the problem here is M is too high. Now this is again I'm telling a very simple example. When you think that if M is too high, number of parking space vacant places is too high, and also another one is that another problem is that if you have to consider that in each state, each counting state, you have defined some more operations. Like here, the states are very simple, just 1, 2, 3 up to M and so on. But if in each state you have to perform some separate operations, and then defining states like this for large M, for a huge M, will be very difficult, right? Because I mean, after a certain bound, you cannot actually take care of it. It will be difficult to take care of each of states separately. So it is one important challenge. One, when we are talking about this FSM-based design, how will I choose the state, or how will I choose what parts I will choose at states? Because once the states or occurrence of the system has been chosen properly, I think after that, this transition condition selection, that is basically just you have to go through carefully the specification, and that can be done. But the first important challenge is how to define the states. And also, in this case, the next we will take one example and see how different types of FSM or extensions of this FSM can help in number of state reduction. And for that, just recap what we have talked about extended state machine. We have already mentioned about that as FSMD, where we are augmenting some data path with our FSM. Remember, there we have, whenever actually we can go to that definition back. See, this is the example. Here we have defined this FSMD model in that way, where we have states, set of inputs, state of outputs, or transition functions and output functions, or initial states, very similar to our traditional FSMD. Only new part we have defined the augmenting some variables, or augmenting one set V, that is set of variables, incorporating this set of variables in our design. So in this example, you see how augmenting this added variable can help you to reduce the number of states. Okay. So again, the same garage problem, smart car parking problem, we will model in a different way. Just go back to see here we have considered this up, down, these are pure or discrete signals, and we have considered count as our output and state this way. In this case, we are defining in this definition. So next, inputs are same, up, down, pure. That is same as the previous inputs. Outputs are also same. So with incorporating this C variable, or we can say this is a count variable, just name it as count, that will help you to understand. We can see that the whole FSM, where we use at least M or M plus 1 states to define our this problem, to model our the same problem. Here I can model this just with one state. that is counting. What I'm doing, I'm checking, I am modifying my guard, or that is my transition condition in this way. Here we can see, we can defining the transition condition is up or not down. Okay. That was also same whatever I have used in my previous condition for up counting. Or I am augmenting another extra condition that is related to the variable that I have introduced, and that's why I'm making this FSM as, I mean, considering this FSM or state machine as an extended FSM. By the way, another thing I forgot to mention, why I am telling FSM, finite state machine. So far we have just talked about SMI means state machine. Finite state machine means we have finite number of states. That's all. So here I am just incorporating these variables and I'm checking whether this is C less than M or not. So now how my state machine is working? It is having some initial value of counting. Now it is checking if it is, I mean, up, there is a detection in the arrival detector. That means up is 1 or not. And down is, it's not down. That means there is no decrement in the down counter. If both of this is getting satisfied, that is means this is AND condition. Along with that, we are also checking another condition, that is my count value is less than M or not. That means M is my maximum number of counts that can, can be present, that the car count that can be present in my parking lot. So whether is my count is within, is less than that or not, within that threshold or not. If that's so, what I'm doing, my next transition is up into that counting. That means I'm continuously counting. Whenever there is any change in this up value or down value, I am just counting. I am retaining in this same state. And what extra I'm doing, see, here you can see what is the advantage of mentioning this action part. I'm just increasing this value C to C plus 1. That means whenever there is an arrival detector up is high, I'm increasing my counter value. Similarly, if I am going to this part, like in the down counting part, if there is some departure detection, then my down is 1, down is high, and not up means together I am checking there is nothing detected in my arrival detector. No new car has entered inside the parking lot. So both the conditions together are getting satisfied. This is quite similar to the previous one, just the control inputs are reversed. And this is C greater than 0. That means my counting input is greater than 0. Then I am again maintaining the same state. This is a self loop type of thing. I'm maintaining the self state. I'm continuing my counting state, and I am setting this value C is equal to C minus 1. That is, I'm decrementing the count. In this way, I can see that just incorporating one single variable C, we have reduced these huge number of states into a single state. In that way, you can see this extended state machine can be very effective when we are actually designing these complex embedded systems. Okay. This is a very important concept. So, is there any question?
Ma'am,
Yeah.
ma'am, the situation, conditions up and down, like
Yes.
there are only two situations here, right? When there is up and not down, and down and not up. Only
Hmm.
two states are being used. Like,
Hmm.
why are we like
Not states.
why not? Yes, ma'am.
First of all, they are not states, right? They are your
Okay.
control inputs, because first that's the way. First, you have to understand what is the control inputs. What are the states? State means when there is something, I mean some detector, arrival detector or departure detector is detecting, and based on that it is setting this control input as up or down. Correct. So these are your control inputs. Based on that, you have to check what your system occurrence, what will be the change in your system occurrence. That means in which state, what was the previous state, or you can consider that whatever is the current state of your system, and based on these control input change, what will be your next state. So that is the objective of our FSM design. So that is first thing you have to understand. That is your control input. Okay, then continue with your question.
Yes, ma'am. The control inputs, like the control inputs, we are getting only when the situation is like either it is up and not down, and the other situation is down and not up. Like, is
Exactly.
there a possibility like there is a condition like not up, not down, or like both? I guess the fourth is not possible. Up
Okay.
and down.
Okay. Up and down. Okay. This is possible. Actually, up and down. Up and down means what? Both your arrival detector is detected that some car is entering inside the parking lot, right? And in your if your down is one means your departure detector also detected that some car has left your parking lot. So if both are, what to say, both are 1-1, then what will happen?
The count remains same.
Count remains same. Exactly. So that means you have to introduce one self loop in these states. Okay, maybe we have not considered that part, of course. That need to be considered. Okay, that is the self loop part we have to give inside the state. But whatever the other possibility you were telling, that is not up, not down. Now, not up means up whenever there is a requirement that some detector, some sensor has detected something, then only we are interested to check what is the input from the other detector. See, when not up means what? Arrival detector has not detected anything. Correct? And
Yes,
for not down also, departure detector also not detected anything. That means your parking lot is in a state where no activity, no event is taking place. So in that case, basically we do not, in case of discrete system, as I have already told, that this is basically event driven. Whenever an event is occurring, event is taking place, then only we are considering what is my present state, and based on that event, where I will go. So not up, not down condition, I do not think, maybe not this case, maybe some other cases we have to consider. But in this case, I do not think it is worthy to consider, because not up, not down means nothing happened. There is no event occurred. So I mean that part, there is no, it will not change anything in the system. So that's why that part will not, probably it will not get considered. Okay.
Okay.
Any more questions? Anyone?
No, ma'am.
No, ma'am.
Ma'am,
Question. Good. Huh? Yes.
ma'am. So every time when we are like moving from finite state machine to extended state machine, what we are doing is like we are making a transition. I mean a variable, and add the transition as the variable, right?
Make it okay. Whenever I'm moving from normal FSM to extended FSM, right?
Yeah.
It is not, no, it is just in this example. It is not that, it is not required that for your extended state machine, yeah. In this extended state machine, it is not always confirmed or always required that you have to make some change in your variable part, or in every state you have to make some changes in this, in your, I mean, augmented variable. No, that is not required. It may happen for some transitions you are actually incorporating this as action. In some transition you are actually incorporating as a part of a guard, because here you can see, right, DC is part of both. DC is a part of here, it is part of guard, it is part of action. But that is not required, or that is not mandatory that DC you have to use in every step, in every guard, in every action. No, it may happen that you have introduced one variable, not even a set of variables, and that is only taking part in one of your transitions. It is highly possible in case of spatial data. And also it may happen that your incorporated variable is not taking part in your any of your guard or any of your actions, but it is taking part in I mean, it is being important as in your final action or final output setting. Because what I mean that you are actually executing different states, and finally you are setting some variables based on those states. That time also, basically in your extended state machine definition, you have incorporated or augmented that particular variable, but that particular variable you have not used in every state. Just you have set the value of that variable in the final state or at your output. That is also possible. So that is not required that you have to use or you have to set value of that variable in every state. Okay?
Okay, ma'am.
Any other question?
Hello, ma'am.
Yes.
Ma'am, can we say that FSM is just a set of instruction and FSMD is instruction with variable? Like the variables are there so that instructions would be acted upon them. Can we say like that?
Yeah, we can say, see, when we are thinking about FSM, yes, FSM means some states. Okay. The states,
Yes, ma'am.
you can think about some Boolean expressions, right? State. How can
Yes,
you
ma'am.
think about this? And these Boolean expressions is changing based on your some Boolean inputs. Okay, those Boolean inputs are your control inputs, like up, like down, like maybe 1, 0, or something like that. So these are mostly prominent. These are most prominent, I mean, modeling for your control-based system. That's why you remember in our first or second slide where we first mentioned about that state-based model. There we have told that this FSM is mostly prominent for control-based systems, where we have very distinct inputs. But when we are augmenting that Boolean expression and Boolean inputs with some added variables, that may not be some Boolean variable, but other type of variables, then it is getting extended, and that's what we are defining as extended FSM or FSMD, whatever you mean.
Yes, ma'am. Okay, ma'am. Yes, ma'am.
Any other question? No, I think so. Whatever you have, please go through this part. This is very basic part, but you will see gradually when we will move on, we will discuss more on top of these concepts. So this is one extension we have considered today in FSM model. In the next case, what we will be discussing, some other challenges when we will be thinking about FSM based model design. And those are very prominent requirements when we think about these embedded system-based applications, embedded system-based networks. So what are these prominent requirements? One is hierarchy, and another, one is hierarchy, and another one is concurrency. Now you can see here three different state machine models. Here are A, B, C. From A, there are some inputs to B, B to, from A1, there is some transition to B. From A2, some transition to B, and so on. And these transition conditions are also well defined. In case of B, the same example, the same states you are having, but with some hierarchy. That means there will be some hierarchy with A1 and A2, and after these execution, based on these X, Y transition conditions, once this hierarchy is first maintained, and then from this hierarchical state or for this level state, you will get some transition input and you can move to some another state to B. So where this is the same example, but in A, there is no hierarchy. Here is some concept of hierarchy. And in this part, you can see there are two concurrent state machine models. Like here, this is C and D. There are two FSM models, where C is having their own state, C1 and C2. C1 and C2, and D in this D state machine model, you are having states D1 and D2. Now these two state machines, they have their own flow, their own transition conditions and whole FSM model, but somewhere they need to interact. For example, we can again go back to our first example that we have started our class, that V2I network, a vehicle to interface network when we are designing. Where you were talking about the smart car or pedestrian, they have their own FSM model. When we are talking about the smart car and your smart signaling system, they have their own FSM, and all these FSMs should run in concurrence, should run concurrently. Also, there may be possibly there may be some hierarchy in between them. So whatever basic definition we have talked about, that doesn't deal with these hierarchies. So that's why we will define with that, starting from that basic definition, we will see how this hierarchy and how this concurrency can be incorporated, and can those models can properly be defined, can properly model with our existing FSM concept. Okay. So this part we will take from next day, because that is another new concept, extension of this concept basically. And so from this part, we will start our discussion from this next day. Okay. So this is all whatever I wanted to discuss for today. So you can ask me if you have any more questions. Otherwise, I will think and give you one assignment. Okay. Maybe in case of traffic, okay, for book we refer for this part. Okay, there are two books with, I'm merging those two books while teaching. One is Frank Vahid and another is Lee Sechia. Okay, so these two books you will find in the drive link, whatever I have shared. You can see there is one book folder. In that folder, soft copies of all these books and some more books also you can find. So those books we will refer later when we'll move on to some other types of models. But mostly this FSM and part we will discuss from these two books. So you can find those soft copy of these 2 books in that folder.
Ma'am, can you repeat the name?
One is Lee's Asia. One is Lee's Asia. Okay, I can show you. One is Lee's Asia and one is Frank Vahid. Okay. I will mail you the exact names of them. Okay. Those are all the name is embedded system design, different approaches, and etc. I will send you those names. And then the books are there, and the soft copy of those books are there with that. Right.
Okay.
Okay. So any more questions? If not, then we can log off for today. Okay?
Okay.
Yes.
Thank you, ma'am.
Yes, ma'am.
Okay.
Thank
Just
you.
go through
Yeah.
the chapters. Yeah. And let me know if you have any questions. We can again take up that. Okay? Bye.
Okay.